Hi, welcome to the coronavirus mathematical model. In this video, we are going to discuss a mathematical model called SIR model in order to model the dynamic spreading of coronavirus. SIR model is a statistical model which is also called as compartment model. Epidemiologically, any infectious or spreading disease can be modeled and analyzed mathematically using compartment model. What is compartment model? Under compartment model, the entire population is divided into number of compartments. In our case, for SIR model, the entire population is divided into compartment of susceptible, exposed, infectious, recovered. Initially, the entire population is assumed as susceptible because it is the best assumption under spreading of diseases. Initially, we doubt everyone, so everyone is going to be put up into the susceptible compartment. After some time, a fraction of people from the susceptible compartment may be moving to exposed compartment. After some time, a fraction of people from the exposed compartment may be moving to infectious. This transition is taking based on the incubation period of the disease. Any spreading disease is having a period of incubation time. Based on that, the number of people from exposed will be moving to infectious compartment. Once the peoples are moved to infectious compartment, there are many dynamic events are happening. For example, a fraction of infectious people may be moved to quarantined compartment because of government action or because of any other external forces. And the people, those who are in infectious compartment and quarantined compartment, may be moving to either recovered compartment or died compartment based on their actions in the compartment. For example, if the people are in the infectious compartment, by taking medicines or because of some other reason, they may be automatically recovered and they may be moved to recovered compartment. Otherwise, the people those who are in infectious compartment, because they are not taken any medicine or they are not having much immunity, they may be moved to died compartment. The same thing will be happen in the quarantined people. They may have recovered because of taken medicine or some other reason, or they may be going to die because of their immunity level are very poor. The SIR model defines the dynamic of the compartments using four ordinary differential equations in time domain with the help of three parameters alpha, beta and gamma. Let us discuss what are those parameters. Where the alpha is the inverse of incubation period, beta is the average contact rate and gamma is the inverse of mean infectious period. Let us define the dynamics of susceptible compartment. The dynamic of susceptible compartment ds by dt is given here, that is minus beta into s into I, where beta is the average contact rate in the population, where s is the number of people in the susceptible compartment, where I is the number of people in the infected compartment. This equation shows that those people in the susceptible compartment is having contact rate of beta will be moved to exposed compartment by the infected people I. The minus sign in this equation shows that those people in the susceptible compartments are moving away from susceptible compartment to exposed compartment with the rate of beta into s into I. Let us define the dynamic of exposed compartment dE by dt. The dynamic of the exposed compartment can be defined by subtracting the number of people infected from the already available number of people in the exposed compartment. Here, beta into s into I shows the number of people already available in the exposed compartment, that is the quantity that is came from the susceptible compartment from the equation number 1. From these already available people, if you subtract the number of infected people, this will give you the dynamic of change of exposed number of people with respect to time. Here, the second term alpha into E is nothing but the number of people infected in the exposed compartment, where the alpha is nothing but the inverse of incubation period. As already we discussed, the number of people going to be infected in the exposed compartment is going to be determined by the parameter of alpha, which is nothing but the incubation period. If the incubation period of the disease is high, then it will give low alpha, which means only less number of people will be moving from exposed to infectious compartment. If the incubation period of the disease is very low, that means very quickly it is going to be spread, then the value of alpha will be very high, which will take more people from exposed compartment to infectious compartment. That means the alpha and E will be bigger number. The dynamic of infectious compartment dA by dt can be defined by subtracting the number of recovered people from the infectious people. Initially, there are alpha into E number of people in infectious compartment, which is coming from the exposed compartment. From this number, if you subtract the number of people recovered, that will give the dynamics of infectious compartment. The number of people recovered is given by the second term, which is nothing but gamma into I, where gamma is the mean infectious period inverse. You can see the number of people recovered is function of this mean infectious period. Suppose the mean infectious period is high, which result in low value of gamma, which in turn make the number of people recovered is less. That means if the infectious period is high, the number of people recovered is less. Suppose the mean infectious period is low, which results in the high value of gamma, which in turn results in more number of people recovered. So this equation shows clearly the change of people in infectious compartment is function of number of people recovered, which is in turn defined by inverse of mean infectious period. As already we discussed, the gamma into I is nothing but the rate of recovery, which is given in this equation 4. Equation 5 gives the constraint of the system where total population N is summation of susceptible, exposed, infected and recovered. This equation clearly shows that the number of population is fixed one from starting to end of the study without any new birth or any migration from one place to another place. And there is another important parameter under the model, which is called basic reproduction number, which is given by the equation 6. It is nothing but the ratio of beta and gamma. This is basically defining how many new infected people will be reproduced over the period of time.